In the previous videos, we used the molar mass equation to do some useful calculations involving chemical formulas of substances. In this video, we will use the molar mass equation to do some very useful calculations involving chemical equations. To do this, we will revisit our understanding of chemical equations and in particular the mole interpretation of a chemical equation. Here we have a chemical equation. It's a balanced chemical equation for the combustion of butane, C4H10, in the presence of oxygen to produce carbon dioxide and water. A mole interpretation of this balanced equation would say that 2 moles of butane will react with 13 moles of oxygen to produce 8 moles of carbon dioxide and 10 moles of water. So if I started with 4 moles of butane, how many moles of carbon dioxide would I produce? The ratio 8 to 2, the stoichiometric coefficient of 8 in front of carbon dioxide and 2 in front of butane, can be used to help us with these calculations. So for example, the ratio 8 to 2, if I started with 4 moles of C4H10, I would get 16 moles of carbon dioxide. If, however, I only started with 1 mole of C4H10, I would only end up with 4 moles of carbon dioxide. That's the same ratio, 8 moles of carbon dioxide for every 2 moles of butane. If I started with 0.5 moles of butane, then 0.5 times 8 on 2 would give me 2 moles of carbon dioxide. So what we've seen here is that the moles of product can be calculated from the starting moles of reactants by using the ratio of the stoichiometric coefficients, and that's crucial in our mole interpretation of a chemical equation. If, however, we wanted not to calculate the moles of product but the moles of reactant required, then I can use the ratio of the stoichiometric coefficients again. So if I had 2 moles of butane, how many moles of oxygen would I require? Well, the answer is 13. We've got the stoichiometric coefficient of 2 in front of butane and 13 in front of oxygen. So if I were to start with 4 moles, we would still use that 13 to 2 ratio. 4 moles of butane, I would need 26 moles of oxygen. If I only started with 1 mole of butane, I would require 13 on 2 moles of oxygen, in other words 6.5 moles. And if I started with 0.5 moles, 0.5 times 13 on 2 equals 3.25 moles. So I can use the moles of a reactant required to react with a given amount of another reactant, and that can be calculated again using the ratio of the stoichiometric coefficients. So in general, if I am given the moles of substance A in a balanced chemical equation, I can find the moles of substance B simply by using the ratio of the stoichiometric coefficient, and the moles of substance B will actually be equal to B on A times the moles of A, where lowercase a and lowercase b are the stoichiometric coefficients of substances A and B respectively. So it's probably best to look at an example. If I was given 0.85 moles of butane, how many moles of carbon dioxide would be produced? Well, the way I do this calculation, I would say that the moles of carbon dioxide equals 8 on 2 times the original moles of butane. The 8 comes from the stoichiometric coefficient of carbon dioxide. That's the stoichiometric coefficient of the substance I'm trying to find information about, divided by the stoichiometric coefficient of the substance I've been given information about, in this case butane. So 8 on 2 times the moles of butane, that's 8 on 2 times 0.85 moles, that's the information we've been given, and we calculate that 3.4 moles of carbon dioxide would be produced from 0.85 moles of butane. So I can do the same to calculate the amount of reactants required. If I had started with 0.85 moles of butane, how many moles of oxygen would be required to react exactly with butane? Here, moles of oxygen, that's the thing I'm trying to find, equals 13 on 2 times the moles of butane, the substance I've been given information about. The 13 comes from the stoichiometric coefficient of the substance I've been asked to find information about, and the 2 comes from the stoichiometric coefficient of the substance that I've been given information about. Moles of O2 equals 13 on 2 times the moles of butane, which is 13 on 2 times 0.85 moles. And that number is 5.5 moles. So I would require exactly 5.5 moles of oxygen to react with 0.85 moles of butane. The problem is, we never weigh out moles in the laboratory. We typically weigh out mass quantities. So what about mass quantities? What if I were given a mass quantity of butane of 5.78 grams and asked to find how many grams, or what the mass of carbon dioxide will be produced? Can I start with the mass of butane and go directly to the mass of carbon dioxide? The answer is no. I can't do that calculation directly. What I first have to do is, if I'm given the mass of a substance and I want to find the mass of another substance, I first have to go through this step of converting that mass into moles. So if I'm given a mass of A, I convert it to moles of A using our molar mass equation, moles equals mass on molar mass, and that would be step one. I would then have to work out, once I've got the moles of substance A, how many moles of substance B I have. And here I use the ratio of the stoichiometric coefficients, the exercise that we've just been through. Once I have the moles of substance B, I then, in step 3, calculate the mass of substance B by using the rearranged molar mass equation, mass equals moles times molar mass. So we have to go through this 3-step process. We've got to convert the mass of substance A to the moles of substance A in step 1. Step 2, the moles of substance A to the moles of substance B using the ratio of the stoichiometric coefficients. And then in step 3, we find the mass of substance B using the rearranged molar mass equation. So finding the mass of a product from a given mass of reactants. We've got 5.78 grams of butane, and we want to know how many grams of carbon dioxide will be produced. Step 1, we need to calculate the moles of butane. The moles of butane will equal the mass of butane over the molar mass. That's our molar mass equation. And that's going to equal 5.78 grams, that's the information that's been given to us, divided by the molar mass of butane. We can quickly calculate the molar mass of butane, C4H10, so we get information from the periodic table about hydrogen and about carbon, 4 times the molar mass of carbon plus 10 times the molar mass of hydrogen, and we get 58.122 grams per mole. We can substitute that into the molar mass equation, 5.78 grams divided by 58.122 grams, and we get 0.0994 moles of butane. So in step 1, we're converting the mass to moles, and we've got 0.0994 moles of butane. Step 2, we now have to work out the moles of carbon dioxide that will be produced. So the moles of carbon dioxide will equal 8 on 2 times the moles of butane that we just calculated. The 8 comes from the stoichiometric coefficient of the substance we are trying to find information about, divided by the stoichiometric coefficient of the substance we've been given information about. that will equal 8 on 2 times the 0.0994 moles that we just calculated in step 1, and that number will be 0.398 moles of carbon dioxide produced. Step 3, we now have to convert the moles of carbon dioxide produced into the mass of carbon dioxide. So the mass of carbon dioxide equals the moles of carbon dioxide times the molar mass of carbon dioxide. This is the molar mass equation rearranged to have mass as the subject. The moles of carbon dioxide we just calculated in step 2 to be 0.398 moles times the molar mass of carbon dioxide. We can quickly work that out. We get information about carbon from the periodic table. We get information from oxygen from the periodic table, and we can work out that the molar mass of carbon is 1 times the molar mass of carbon plus 2 times the molar mass of oxygen, which gives us 44.09 grams per mole when we restrict that to 4 significant figures. We substitute that into this equation, 0.398 moles times 44.09 grams per mole, and we get 17.5 grams of carbon dioxide produced. So we started with our 5.78 grams of butane. Step 1, we calculated the moles of butane and found that that was 0.0994 moles. In step 2, we used the ratio of the stoichiometric coefficients to calculate the moles of carbon dioxide, and we found that that was 0.398 moles. And then in step 3, we converted the moles of carbon dioxide to mass of carbon dioxide using the rearranged molar mass equation, and we found that to be 17.5 grams of carbon dioxide. So this diagram here gives you a very good guide as to solving these stoichiometric calculations involving chemical equations. If you're given the mass of A, then you need to do step 1 to convert it to moles of A. Step 2, you convert the moles of A to the moles of substance B using the ratio of the stoichiometric coefficients. And then step 3, you'll calculate the mass of substance B using the rearranged equation, mass equals moles on molar mass.